Okay, morning class. So we have to start on time every week because those attending online, please mute your mic. But if you have any question, you can switch it on and ask any questions you like. So, but during classes, please mute your mic first. So we will start on time as we have lots of materials to cover in every tutorials, right, including some reviews before we start the tutorial class. And today we're going to discuss about tutorial 2. Okay, let us review some of the concepts that we have discussed in the last tutorial, namely nodal analysis. Nodal analysis mainly consists of 3 main steps. Firstly, you assign node voltages with respect to a reference node. Now, reference node is referring to, for example, this node which is connected to ground. Okay, and then all the node voltages are defined with respect to this reference node. Okay, in this case, for example, over here we have one unknown node voltage, right? And you can assign this node voltage, let's call it V. Okay, there's another node here, but this is a known node voltage, right? It's not unknown in the sense that we know that this is 12 volts. Okay, because this is connected to ground, and here there's an increase in potential by 12 volts. Therefore, this node voltage.
Hello, Prof. We can't see your screen.
Okay. I thought I've just shared it. Okay. Any problem, just let me know. Now, is it okay?
Yes, you can see it now. Thank you.
That's good. Let's start all over again. Okay, I was reviewing nodal analysis, which was actually discussed in the last tutorials. It consists of 3 main steps, namely assign node voltages, Okay, then obtain the equations by KCL, solve the equations. For example, in this simple circuit which we have discussed in question 1 of the last tutorials, okay, we can also use nodal analysis instead of the method that we learned last week. Okay, firstly, nodal analysis says that you assign node voltages with respect to a reference node. And over here, we have a reference node which is connected to ground, 0 volt. Everything is with respect to this reference node. Okay, for example, over here, if you put a node voltage V, it means that it is V with respect to ground. Okay, and similarly, over here, we have a known node voltage of 12 volts because there's a voltage source here, and it is an independent voltage source, okay, of 12 volts. Okay, in the sense that if this is 0 volts, there's an increase in potential by 12 volts. So 0 plus 12, right? Increase by 12, you get a positive 12 over here. Okay, this is considered a known node voltage. You can also assign it as V1, then V1 is equal to 12 volts. Then you solve for V2. But I'll go directly to assign only one node voltage V, because one unknown node voltage V, because this is basically known. So the purpose of this nodal analysis is to find out what is this unknown node voltage by obtaining the equations using Kirchhoff current law. Now, Kirchhoff current law says that the current entering and leaving the node must be the same. So therefore, you can write down the equations by looking at the current entering and leaving the nodes. For example, I will assign this way: current entering from the source. It's likely that it is correct because current will leave from the positive terminal. Now the other two is likely correct if V is positive because it will flow from a higher voltage to 0 volts, right? Even if I have assigned wrongly, what will happen is that you'll get a negative values, which tells you that it should be the other way around. So at the beginning, we really do not know what will be the directions. We just assume a certain directions, and then we look at the answers. If the answer is positive, it means that the directions we assume are correct. If not, it just means that it should be the other way around. So this is the first step, assign node voltages. After that, you use Kirchhoff current law to write down the equation in terms of the unknown node voltage, right? In this case, only one. And if I take Kirchhoff current law at these nodes, then I can write down my first equations. 12 minus V is the voltage drop across the 4 ohm resistor. Ohm's law says that if you divide the potential difference by the resistance, you get the current flow. So this is the current inflow. And we have the current outflow, which is V minus 0. This is voltage V minus, right, the reference, which is 0, divided by 6. And actually, you should just write down V divided by 3 or 6 directly, right? Because the other one is 0. V minus 0 is V divided by 3 is this current. Now, this is actually your current IX. So later on, once you have found your node voltage V, divide by 3 will give you IX, which is what we wanted to find, right, in the last tutorial. And you can see that in circuit analysis, the method is not fixed. You have many basic methods to use, and which one to use is very much depending on the circuits, the particular circuits itself. For this particular questions, you can see that using nodal analysis is good because there's only one unknown node voltage. Therefore, you only need one equation. Okay, the lastly is to just do algebraic manipulations to obtain V, right? So this is to solve the equations to obtain the unknown node voltage. And this is a review of nodal analysis. Today we move on to a related topic, mesh analysis. Okay, nodal analysis is to find out the
Sorry, Prof. You muted yourself.
Is it just or just only,
Yeah,
right? Okay.
just only.
Somehow Okay, that's good. So then I'll just continue. So over here, mesh analysis is basically the reverse, right, of nodal analysis. Here, instead of node voltages, we find mesh current. Instead of Kirchhoff current law, we use Kirchhoff voltage law, right? And 3 main steps also. The idea is the same. In order to find out the mesh currents, you need to assign. In circuit analysis, anything that you do not know, you assign a variable, and then you try to write down some equations to solve it. Okay, if you look at the same circuits again, I can assign 2 mesh currents, right? This is 1, this is 2. Which directions? Any direction. For example, clockwise, right? Or anti-clockwise, it's up to you. Okay, if I assign both clockwise, this actually means that I'm looking at this current over here. This is I1, and this is I2. Right? Take note of that. Okay, and basically, in this branch, right, as far as this branch is concerned, there's only I1. Right? This is also I1. And this is I2. This is also I2. Now, similarly, this is also I2. Okay, but at the common branch between the 2 meshes, the current would not be the same. Correct? Would not be the same because according to Kirchhoff current law, when the current enters this node, it will split into 2. So if I assume downwards directions, following this path, then this current would be I1 minus I2, correct? I1 minus I2. Because if I add these two up, you get I1. That means inflow equal to outflow. Current flow into the node must be equal to the current leaving the node. This is Kirchhoff current law. Okay, basically this is I1, I2. There's a faster way of writing this I1 minus I2 by looking at the directions of your mesh current which you assign. Now this is downwards, so it's in the same direction. We put positive. This is upwards, right? In the reverse directions of the directions that we are interested, then is negative. Okay, if you are confused, you can just use Kirchhoff current law at this node. You can also write down this branch current. Now, here I'm doing the first step. I assign 2 unknowns, I1, I2. Okay, if you have 2 unknowns, then you need 2 equations. Therefore, we move to the next step. We obtain the 2 equations by applying Kirchhoff voltage law at each of the mesh with the unknown mesh current, right? That means that this loop and this loop. Okay, I'll just show you one. If I start from this point and I move around this loop, right, following this clockwise directions, then from here to here, there's an increase in voltage of 12 volts. Okay, and from here to here, this is a passive component. There's a drop in voltage. According to Ohm's law, is resistance times the current flowing through it. So it's 4I1. When you come to this 6 ohm, write down 6 ohm first. The current flowing through it, right, is not I1 anymore. It's I1 minus I2. So we write down either I1 minus I2. And then you're back to the same point. So it's equal to 0. Now, similarly, you can write down another equation by moving around I2. In this case, if you're moving clockwise directions, then your current should be this way, right? Should be this way. So therefore, it will become negative 6 I2 minus I1. Okay, if you're confused, you just do a Kirchhoff current law here. Inflow equal to outflow. Therefore, this one, right, should be I2 minus I1 in the upward direction. Okay, because these two added up will become I2. Then you can write down another equation. So the whole idea is that I form 2 equations, then I solve the equations to obtain the mesh current. Okay, you can see that the idea is basically the same. Anything that you do not know, you assign a variable. Then you try to write down, right, the equations by applying circuit's laws, Kirchhoff voltage law, Kirchhoff current laws, and after that you solve the equations to obtain the unknown mesh current. Okay, for this same circuit, you can see that it is better to use nodal analysis because you're only solving one equation. Well, for the mesh currents, you're solving two equations, right? So the method is not fixed. I would suggest that if you're free to choose any method, decide by looking at the number of variables that you need to solve. Okay, in this case, nodal analysis is better because you solve for one equation, but for mesh analysis, you can also similarly solve it, but a little bit more work should be done by solving two equations. And this is very much depending on your circuits. Okay, for example, if I replace my voltage source by a current source, I say 6 ampere, then in this case, it is actually better to use mesh analysis. Why? Because mesh analysis says that you want to know the current. In this case, you really know that this is 6 ampere, which means that the only mesh that you need to assign is this one, right? Which is basically your IX. You can call it IX or I1, it doesn't matter. And this basically means that I will only go one loop and I will be able to write down one equation in terms of IX. I can solve it directly, right? For this current, right, take note that because this is 6 ampere, this is known. So mesh analysis, anything, right, with a known current is good. For nodal analysis, anything with a known voltage is good, right, with respect to the reference. That means that one answer is already provided. If this current is already known, you need not write down the equations anymore, correct? Because you have already given the mesh current. It means that you do not need to write down any equation to solve it anymore. So do not do KCL over here, Kirchhoff voltage law over here, but do Kirchhoff voltage law here only. Then you can write down one equations in terms of IX, okay, and then you solve it. Okay, I was saying that this is 6 ampere, and this is IX or I. Therefore, if you go this direction, that means you apply Kirchhoff voltage law clockwise, it's upward directions, and this current should be IX minus 6, correct? Inflow equal to outflow. These two added up become IX. Okay, which means that you have IX minus 6 times 6 voltage drop across here. Then 3IX voltage drop across here, you come back to 0. You write down one equation, you can solve for IX, right? So for this circuits, it's better to use mesh analysis. For this circuit, it's better to use nodal analysis. Okay, I'll suggest that you take a look at what method to use before you start solving it. Some of you are told to just use mesh analysis, but that's not good in a sense that even though you can solve it, but it could be more complicated sometimes, right? So it depends on the problem. Okay, but in actual fact, mesh analysis consists of more details in the 3 steps. Okay, that's because a circuit is not fixed. It can have many forms and many designs. So we have to just remember the 3 basic ideas. And after that, right, the rest are just some slight variation. For example, assign mesh currents with respect to the mesh. And just now I show you a mesh current is known, right? If there's a constant current source exists in only one mesh. For example, this, it means it's known. Therefore, you only need to assign this mesh, right? So this is what it means. You can read through your notes again. You can find all these details, right? Hidden inside somewhere. Okay, I'll just summarize this in a more formal way, and I provided this summary in your lectures website, E2001. You should review it after reading through your lecture notes, and of course the lamps, right? It will only be useful if you have gone through that, and then you read the summary. You can't actually extract information from a summary. It's too brief. But if you read through this and go through your notes again, right, you will find that everything makes sense because you basically just follow these few steps. Okay, and this few steps has a meaning. It's not something which is fixed, right? It's an idea, a methodology which you should follow and not remembering as the steps or formulas. Okay, so first you assign mesh current. Why? Because you want to find out what are the unknowns, right? If it's known, then no need to assign. Secondly, you obtain the equation by Kirchhoff voltage law. Now this part is important. The main idea is to express everything in terms of the mesh current. Why? Because you want to get equation in terms of the mesh current. So anything which is not expressed in terms of the mesh current, you try to relate it to the mesh current so as to write down the equations. Okay, here, sometimes when you apply Kirchhoff voltage law, right, Kirchhoff voltage law, for Kirchhoff voltage law, if you have a voltage source, this is okay because you just write, for example, okay, here, there's an increase in voltage, you can either write positive 20 or you want to write the other way around, is okay. Because A plus B equal to 0 is the same as negative A minus B equal to 0, right? No difference at all, which means that you have to follow one convention. If increase, you put positive, then the rest increase will be positive. If increase, you want to put negative, it's also okay. This means that for your resistors, right, you want to put on positive. Okay? You want to put all positive, then in this case, you just follow the same convention. Okay, as I explained to you last week, you can view Kirchhoff voltage law in 3 ways, right? Increase in voltage equal to drop in voltage, or you reverse it by multiplying by a negative number. You look at the other way around, it's also the same. Okay, here, voltage source is okay, but current source is not okay when you apply Kirchhoff voltage law. Why? Because Kirchhoff voltage law says that I want to know the voltage drop. But current source, I know the current, I do not know the voltage. How about resistor? Resistor, I do not really know the voltage, but I can express them in terms of Ohm's law, right? Which means that I express in terms of the mesh current. Okay, but this voltage across this source, current source, cannot be expressed in terms of the mesh current. And therefore, I have a slight problem here. When I write down the equations using Kirchhoff voltage law around mesh 1 and mesh 2, okay, in the sense that I have this unknown node voltage, right, which I cannot proceed any further. This also means that you have one more unknown. Okay, but there's a simple way to overcome this problem. If you add these two equations up, then this V minus V, right, cancel out each other, and you have one equations with only I1 and I2, which is what we want, right? We want to get an equation in terms of I1 and I2 only. Okay, but the problem is that you have combined 2 meshes into one, and therefore you need to look for one more equation because you have 2 unknowns, right? If you have 2 unknowns, namely I1, I2, you need 2 equations, but because of this current source, you have combined into one, and you need one more information. Okay, I'll come to that later on. Okay, another way of looking at this combinations of 2 meshes is actually a simple illustrations over here. Okay, if I start from here, I want to go around this loop. Right? So this is the usual way. When I come to here, I should come down. But however, because this voltage is not known, so therefore I should avoid this path. Okay, which means that I should take a longer path. Okay, if you take a longer path, you still can come back to the same point. Okay, that means that I write down another equations by going one big round, which combine the 2 meshes together. That's why it's called super mesh. And at the same time, I can write down one equations in terms of I1 and I2 only. Now, if you look at it this way, you can write down this equation directly without writing these 2 equations and combine them. Here, negative 20, then you have 6I1, right? This is 10I2, 4I2, Then you come back to this point, okay, which means that this is easier. So the concept of super mesh is to avoid the path with unknown voltage, right? With unknown voltage, namely a current source. Now, this current source, right, even though the voltage is not known, but the current is known. The current is known. So you should make advantage of that, right? Namely, I want this current, right, to be expressed in terms of I1 and I2, in the sense that, right, upward directions is I2, all right, downward directions is I1. So I2 minus I1 is actually 6 ampere. Okay, if you are confused, you just take Kirchhoff current law here. This is I2, this is I1, correct? So inflow equal to outflow, meaning that I2 inflow is equal to outflow, which is I1 plus 6. This is exactly the same as this equation. Okay, therefore, this is my equation 2. Now, having obtaining two equations, you can then proceed to step 3, solve the two equations with two unknowns by using any method. So this is the main idea for mesh analysis, and we are now ready to solve problem 1 of this tutorial. Any questions so far? Okay, let's look at this circuits. Now, firstly, right, over here, there is a current source, right? There is a current source. Now, as I said, current source, it just means that the voltage is not known. Okay? The voltage is not known. We do not know this voltage, but on the other hand, it also tells you that this current is 3 ampere, right? 3 ampere. And in this circuits, the currents are already assigned to you. I just want to stress that this means that this is I1, this is I2, and this is I3. Right? Now, if this is I2, and this is I3, and this is 3 ampere, therefore, if you use Kirchhoff current law at this node, inflow equal to outflows, you can get one equation easily, right? I2 plus 3 inflow is equal to I3, right? I2 plus 3 is equal to I3. So this branch actually gives you one equation. So we have one equation from here. Okay, another equation can be obtained from here, right? Mesh 1. And another equations can be obtained from super mesh. Okay, why do we do super mesh? Because we avoid this branch with unknown voltage, right? If this voltage is unknown, you cannot write down an equation in terms of I1 and I2 using Kirchhoff voltage law, but we take a longer path and everything can be expressed in terms of I1 and I2, correct? And then you get another equation. So this is an overview. This is how we'll do it. We apply Kirchhoff voltage law around mesh 1, and when we are trying to use Kirchhoff voltage law along mesh 2, we found that there's this unknown voltage. Therefore, we take a longer path and we come back to the same point. We get one equation by combining two meshes. Okay, the last equation can be obtained from this branch current, because even though the voltage is not known, the current is known, and it can be expressed in terms of I2 and I3, right? So the key idea is that everything can be expressed in terms of the I1, I2, I3. Okay, including this V0. Now, this is V0. This is I1. This is I2. And V0 is actually this current multiplied by 2. And what is this current? This current is actually I1 minus I2, right? I1 minus I2 flowing downwards, passive, right? Flow from high to low. So V0 is I1 minus I2 times 2. Okay, which means that when you come to this one, you multiply by 2 times of this, then everything can be expressed in terms of your mesh current. All right, let's look at the details. I'm only providing an overview. Okay, I will follow these steps, right, to solve this problem in this tutorial. Firstly, you assign mesh current. I1, I2, I3. For this question, is already assigned for you because this is the beginning of the tutorial. But in actual fact, you must assign it by yourself, right? You must assign it by yourself. If it's unknown, you just assign. If the current is known, then you just mark, right, that is equal to that value. Okay, after that, obtain the equations by using Kirchhoff voltage law, starting from one mesh, right, at a time. Okay, if I start from mesh 1, okay, namely that I start from any point, okay, here there's an increase in voltage, so I put plus 12, right? If you want to put negative, it's also fine. When you come to the voltage drop, then you put positive across the resistor. Okay, over here, ignore this one first. Okay, we are simply going around this loop only, right? Going down this loop by expressing everything in terms of I1 and I2. So this will only be used later on when you encounter this dependent source. At this stage, you just go around this loop, write down the equations. Here 2 ohms, passive sign conventions, right, from high to low, current flow from higher potential to lower potentials, right? So there's a drop in voltage here, and then the current here is I1 going downwards, I2 flowing upwards. So I1 minus I2. Okay, if you are confused, as I said, just write down this one. This is I1, this is I2. Then take Kirchhoff current law at this node. Downward directions, right? You want to follow this path. Downward directions, it should be I1 minus I2. Then times 2 ohms. It's the voltage drop across the 2 ohm resistors. Okay, next, when you come to this branch, the current is not I1 minus I2 anymore, right? Be careful. This is I3. And this is I1, right? Therefore, downward directions, I follow this path. Downward directions, this should be I1 minus I3. Inflow equal to outflow. A faster way to write is that I1 is downwards, positive. I3 is upwards, negative, right? Therefore, you can write this down and you come back to the same point again. Okay, this gives you 1 equation, right? It's not enough because we have 3 unknowns. 1, 2, 3. You need 2 more equations. Okay, but if you proceed to this next mesh, okay, you can see that there's this current source over here. Right, therefore, this means that I need to apply the concept of the super mesh. Right, which says that I need to avoid this one by going one big round. Okay, this is called super mesh. Combine 2 meshes into one. Okay, I still can fulfill this idea. Write down an equation in terms of the mesh current, right? By avoiding this unknown voltage. Right, this voltage is unknown. So we write down these equations by going round the loop, right? Any point, start from any point. For example, here, negative 2. Now here you are going this direction now, upward directions. So I2 is positive, I1 is downward, is negative. I2 minus I1 multiplied by 2, right? And there's a voltage drop. Okay, here there's only I2, this is I2, so negative I2. And over here, there's a drop, right? Positive to negative drop of 2V0. Finally, when you come to here, I3 is upwards, I1 is downwards. So I3 minus I1, because I'm going this direction, right, equal to 0. Okay, but here you have a slight problem because this is V0. But I need to express everything in terms of the mesh current, right? Because I want to get the equation in terms of I1, I2, I3 only. When you see this, try to trace back where is V0. V0 is here. It's just the voltage across a 2 ohm resistor. Okay, therefore, I should find this current. right? Which is I1 minus I2. I1 is this directions, I2 is in the opposite directions. Multiplied by 2 ohms is equal to V0. Then when you substitute this into here, you get the equations with only I1 and I2 and I3. So I get another equations, which is from the super mesh. Okay, but as I mentioned just now, by using super mesh, it means that you have lost one equation by combining two meshes into one. Okay, but fortunately, we can still obtain the other equation by this branch current, right? Even though the voltage is not known, the current is known. This current is known. So this is called the constraint equations. Right? You can do this as I've shown it to you just now. This is I2. This is I3. This is 3 ampere. Kirchhoff current law says that inflow equal to outflow. You can write down these equations, right? I2 plus 3 is equal to I3. Therefore, I3 minus I2 is equal to 3. Okay, the other faster way to do it is that this is I3, these directions, in the same directions of 3. This is I2 in the reverse directions, right? So I3 positive minus I2 reverse directions is equal to 3 ampere, right? In the same directions as 3 is I3, in the reverse directions, right, is I2. You can write down this equation. Now look at this. You have obtained 3 equations for the 3 unknown mesh currents by Kirchhoff voltage law, right? By Kirchhoff voltage law. So let us look at the overview. Assign mesh currents I1, I2, I3. Then start from mesh 1, we obtain 1 equations. But when we try to go to mesh 2, we know that there's unknown voltage here, which cannot be expressed in terms of mesh current. So we proceed on to avoid this by a super mesh. Right, so this is equation 2. Okay, after that, we obtain the constraint equations by using this branch current. Even though the voltage is not known, but the current is known. Right, so this is one good thing, the current is known. In fact, you can see super mesh is easier. You just go one big round. Right? It's just that you have to write down more voltage drops. Any questions so far? And after that, solve these 3 equations with 3 unknowns using any methods. So I hope everybody can get the ideas. In circuit analysis, anything you do not know, you just call it a variable. I1, I2, I3 for current, V1, V2, V3 for voltage, right? And then you try to express equations in terms of the unknown variables by writing down some equation using either Kirchhoff voltage law or Kirchhoff current law. The whole idea is to express the equation in terms of the variables that you want to solve. Okay, anything which is not expressed directly in terms of them, try to relate to them. Okay, in some cases you cannot, like the super mesh or super nodes, right? It just means that you combine them into one. Then you have to look for another information, right, from the source which is causing the problem. And then after that, once you have obtained enough equations, you solve them. Now, if the variable is known, right, you do not use Kirchhoff voltage law at that loop, right? If the current is known, you just apply Kirchhoff voltage law at the unknown mesh current, right? At the meshes with the unknown mesh current. So the keyword is the unknown. Okay, solving the 3 equations, I'll just show you a brief one, but I expected to know it, any method, so I just got to be familiar with at least one method so as to solve it. Okay, and in examination, as far as examination is concerned, now even though you can nowadays get some calculators, approved one of course, to solve these 3 equations easily. Okay, but in circuit analysis, right, take note that it's quite easy to make mistakes in terms of writing down, right, the equations. One sign wrong, everything wrong. And simplifying it also may lead to problems. So I suggest that first you spend a lot of time checking the first equation, right? When you write it down. Okay, after that, spend time simplifying them. Because if one sign wrong, everything is wrong. Now, in terms of assessment, of course, this is just losing marks, but you have to understand that as electrical engineers, wrong calculations of all this can lead to serious, right, safety issues. So we got to be very precise, right? Spend time to check it, because this could lead to very serious consequences, right, in real situation. You check the equation carefully and they are correct, then solve it, right? As I was saying, even if you can solve it by calculators, write down the main steps so that if something wrong, right, you have something to fall back. For example, one equation wrong, if you just write down one step, then everything wrong. But if you show that you can understand how to solve it, then basically you can have something to fall back, right? Okay, here I'll solve this three equation. I'll substitute equation 3 into 2 and 1. Why? Equation 3 has only two variables, which means that I can express I3 in terms of I2 or I2 in terms of I3. And if you sub into the other two equations, then you eliminate one variable, right? For example, if I express I3 in terms of I2, then all the equations will not have I3 anymore. It will be only I1 and I2. Then I get one equation in terms of I1 and I2. Similarly, if I sub 3 into 2, in equation 2, there will only be I1 and I2 because I've eliminated I3, right? Then you have two equations with two unknowns. You just substitute one into the others. And finally, you can get the variables. Once you get one of them, then you back substitute into the rest. You can solve the rest. Right? So you can try it by yourself, right? As I said, in circuit analysis, do not just read solutions. Okay, you are only okay if you can solve all the tutorial problems without referring to the solution, right? If you read, then it's not a tutorial anymore, okay, which means that you are lack of practice, right? Lack of practice, meaning that you do not have the chance to verify whether you have understood the concept correctly or not. So tutorials are good ways of verifying, right, whether you have understood all the concepts clearly or not, because you have answers, you even have solutions, right, for you to refer to.
Sorry, can you go back one slide?
Sorry?
Can you go back one slide? I
Yeah.
just want to see how to derive the equation for the super mesh. Thank you, sir.
Right, so super mesh is basically to go one big round, avoiding the branch with the unknown voltage and cannot be expressed in terms of the mesh current, right? Any questions? Someone want to ask something? Okay, if not, we move on. Now, week 1 and week 2, you learn a lot of basic tools which you will use over and over again, right? Not only for this course, but subsequent course, right? And as an electrical engineer subsequently. And source transformation is one of them. It is a good way of simplifying circuits by transforming a voltage source in series to a current source in parallel, right? Okay, why do you want to do that? Because sometimes your resistor, for example, cannot be simplified. Therefore, you just transform it so that it can be simplified, right? For example, in this case, I can transform the voltage source in series to a current source in parallel. Okay, after that, I may be able to simplify the circuits further. Okay, the transformations you can remember this way is basically Ohm's law, right? It means that how do I transform the circuits from one form to the equivalent form? Now, in this case, you are given what? Voltage and resistance. You want to find current, right? If I'm going this way. So Ohm's law says that V divided by R give you current, okay, which means that given this, divided by this, you transform it to the equivalent current source. As for resistor, it remains. It's just that the configuration changed from series to parallel. Now you want to look at the other way around. Now it means that you're given current, you want to find voltage. Then you use V is equal to IR. Right? So I times R give you the voltage and resistance same values, but change configuration from parallel to series. So it's very easy to remember, right? Just look at Ohm's law. Remember the configuration: voltage series, current parallel. Okay, I'll use this simple circuits again. Okay, to show you that for simple circuits there are many ways of solving the same problems. Okay, I will transform this voltage source in series with a resistor to a current source in parallel with a resistor. So given voltage, I is equal to V divided by R. V is 12, R is 4, so I get 3 ampere, right? Resistance, same thing, but it's now in parallel. Now, you can see that once I change the configurations, I can apply current division law directly, right? Directly. And remember current division law, if I'm interested in this current, which is Ix, then I take the conductance of that branch, 1 over 3, divided by the total conductance, 1 over 6, 1 over 4, 1 over 3, multiplied by the inflow, 3 ampere. This means that the 3 ampere is split, right, according to the ratio of the conductance. And you can check that this answer will be the same as what you have obtained in last week's tutorial. So this is a nice thing about source transformations. In fact, you can see that here I cannot simplify these two resistors. If I transform into this form, I can simplify these two resistors, right, to be in parallel. That also can. And then you apply current division law with two resistors, right? This is another method, but for more than two, actually, you can just do it directly by using this, okay, which I have discussed in the last tutorial. Any questions? Okay, let's look at question 2. We want to find Ix. Now be careful. When you want to find this Ix, do not use source transformations to transform this, right? Once you transform it, this is not the Ix you want to find anymore, correct? Because you transform it into another form. So the whole idea is that you transform this one, right? Do not transform this, transform this, okay? Okay, I say again, the variable which you want to find, do not transform. Once you transform, you basically change what you want to find, right? So transform those that on the other side to equivalent forms so that your Ix remain, right? Remain the same. And this means that I transform this remaining part into one equivalent forms, and I use this simplified circuit to find Ix. Okay, let's look at the overview. Right? Do not worry about the details first. Just look at how we can solve these problems, right, with this overall planning. Okay, I will start from the right, and I found that there's a source, right? This means a current source, but it's a dependent source in parallel with a resistor, correct? So this satisfies the requirement. So source transformations, a current source in parallel with a resistor. Therefore, I can transform it into a voltage source in series with a resistor. Okay, after that, I can simplify these two resistors by adding them up. Okay, here you can't simplify anything, now you can. And then it becomes a resistors of 50 ohms. Okay, and you use another source transformations to transform it from a voltage source in series with a resistor to a current source in parallel with a resistor. Then after that, I can simplify these two resistors into 25 ohms. Then I transform it from a current source to a voltage source again. So the thing is that I simplified a circuit with 3 meshes into just one, right? Into just one. Then I can apply mesh analysis of one loop only. Now over here you need to do, right, probably 3, right? Or if you want to use nodal analysis, you assign node voltages over here and here. This is known, correct? So either method is fine, but one of them would be simpler, so you have to decide, right? But this question says use source transformation. So we can only use source transformations, and these are the suggested way. Okay, we transform it from one form to another, and finally we have only one mesh. Then we apply mesh analysis, assign mesh current Ix, apply Kirchhoff voltage law, write down the equations, and we can solve for Ix. So this is an overview. Let's look at the detail now, starting from the first one. Okay, in the first step, I need to transform this mesh, this current source, this is a dependent source, 0.5 Ix current into voltage, right? Given current, multiply by the resistance, Ohm's law, you get a voltage. So this multiplied by this, give you 5 Ix. Okay, the most important thing is the sign. Now take note that current always flow out from the positive terminal, right? Current always flow out from the positive terminal. So when you transform to this voltage source, positive sign should be here. Follow the directions of the current. Okay, then we have a 10 ohm resistors, and it is now in series with 40 ohms. Therefore, I can add them up. Okay, if I add them up, then I get 50 ohms. Correct? This is 50 ohms. I can then transform this voltage source in series with 50 ohms into a current source in parallel with 50 ohms. This means given voltage, right, 5 Ix divided by 50, D over R is I, you get 0.1 Ix. Right? So this is 0.1 Ix. Important thing is the direction. The current should flow this way, right? Downwards. So I have a downward directions of a current source, and I have a resistors of 50 ohms in parallel with it. Now the nice thing now is that I can now simplify these resistors. 50 in parallel 50, as I told you, means half, right? Same values, half, 25. Even if you use 50 times 50 divided by 50 plus 50, it also means 25. Okay, and this one is a current source. Given current, multiply by the resistance, 25, R, right, IR, you get 2.5 Ix. Be careful of the sign. Current come out from the positive terminal, right? And therefore, what we have done is that we have managed to simplify the circuits from 3 meshes into only one through a series of source transformation. Any questions so far? Then circuit analysis becomes simpler, right? Rather than dealing with 3 meshes, we have only one. And this means that I can now use, for example, mesh analysis, one mesh. This is my Ix. Right, this means this current is Ix, which is the current which I want. Then apply Kirchhoff voltage law around this loop. Right, plus 60, 15 Ix, voltage drop across 15 ohm resistors, voltage drop across 25 ohm resistors, and come to here, there's an increase in voltage, negative to positive, right, plus 2.5 Ix equal to 0. There's only one unknown. Therefore, you can solve it directly, right? Because there's only one loop. So Ix is equal to 1.6 ampere. Any questions? Okay, if not, let's move on to question 4. Now, question 4 is dealing with another tools, right, to simplify the circuits. Okay, just now we have seen source transformations to simplify the circuits in a form which is easier to analyze. This questions involve a concept called Thevenin's equivalence, right? Thevenin's equivalence circuits is just another way of simplifying the circuits. It is especially important in the calculating the maximum power. Okay, let's look at these questions. Now, in this question, it says that you have an unknown resistor, right? Which means you need to design. What is the design criteria? Design RL so that maximum power can be delivered to this load, right? Delivered to this load resistor. That means that what should be the matching resistance values so that I can draw maximum power from the remaining part of the circuits, right? Now, it's not easy to analyze this circuit directly to obtain the maximum power. Okay, one way is to transform it into this equivalent form. Okay, that means that if this is my load resistance, RL, all right, I transform the remaining part into one equivalent form. Okay, after that, when I connect back my load, the circuit analysis becomes easier. The same thing, there are three meshes there, is turned into one by this equivalent form. Okay, and this equivalent form, you can analyze it easily. For example, what is the current going through this load? I is equal to VTH divided by RTH plus RL, correct? Then power is equal to I square RL, power delivered to the load. L is the load. And I is equal to this. Sub this into here, you get the power in terms of VTH, RTH, as well as the load resistance. So the question here is that, what is the value of the load resistance that gives you maximum power, right? So what is the value of this load resistance which will give you maximum power? Now, here, if you look at this equation, power is expressed in terms of RL. Okay, firstly, if RL is equal to 0, then power is equal to 0, correct? So this is this point. It's obvious because RL equal to 0, no matter what current, you will not dissipate any power, no dissipation. Okay, the next thing is that when RL goes to infinity, I mean very, very large, then your power also tends to 0, correct? Because here the denominator is RL squared. If R is very, very large, then it's larger, much larger than RTH, so it's approximately only equal to RL squared. Okay, then you multiply by RL. It cancels out one of them, but it's still inversely proportional to RL. Okay, which means that this is basically equal to, approximately equal to VTH squared divided by RL. So RL tends to 0, you got 0. Now power is always positive. If it starts from 0 and end at 0, there must be a turning point, right? There must be a turning point. It means that there must be a maximum value because initially it's increasing, but after a certain value it's decreasing, right? It's decreasing because of this relationship, and we need to find out what this is maximum value. Now, to find the maximum value is to find the gradient of P with respect to R equal to 0. So in your notes, you can check, basically you differentiate your P with respect to RL, equate to 0, right? 0 gradient at the maximum point. Then actually it can be shown that by equating this, solving these equations, it means that my RL should be equal to RTH. It basically means that when my load resistance is equal to the impedance, equal to the equivalent, right, Thevenin's equivalent resistance, then there will be maximum power, right? It occurs at this point. And the maximum power is VTH squared divided by 4 RTH. Okay, normally power is V squared over R, correct? V squared over R. Now, why there's a 4 here is actually because the matching conditions, right, is actually equal to RL equal to RTH. So you want to calculate your maximum power in terms of RTH, correct? RTH and VTH, and this 4 will appear. Okay, if you look at these equations, it's easy to understand. When RL is equal to RTH, then these two have equal resistance, correct? Then what is your I? I will be VTH divided by RTH plus RTH, 2 RTH. Then what is I squared? I squared is VTH squared divided by 4 RTH squared. RL is equal to RTH, multiplied by RTH, you get V squared over 4 R, right? So remember that there's a 4 there because we want to express in terms of this and this. See? Now if you directly use your load voltage, VL, then it's just VL squared over RTH, right? VL squared over RTH, but you can check that VL is half of VTH because these two resistors are the same. Then you still end up with this one, right? Any questions? So next, we need to use Thevenin's theorems to simplify the circuits to its equivalent form. And it involves actually 3 main steps. First, you remove this load. Okay, then find VTH and RTH based on the circuits without this load, right? Based on the circuit without this load. And after that, once you have found the equivalent form, you connect back the loads. Then you analyze the circuits based on this load. Okay, not only that it is useful in finding maximum power, okay, this circuit is also useful when your load changes frequently. For example, if I ask you to find the circuit variables when R equal to 1 ohms, 5 ohms, 20 ohms, right, and 100 ohms. Okay, one way is to do your circuit analysis a few times with different values. The other one is to transform the remaining fixed part into an equivalent form. Then over here, even if you change your values, you can do the analysis very easily, right, to find out the current flowing through this resistor. So Thevenin's theorem is very useful in simplifying your circuits to a simplified form so as to find the variables, the load variables which you are interested. Now there will also be a lab, right, related to these Thevenin's theorems, and in that lab actually your circuit is a black box. Okay, in many commercial products we know that it's protected, so you can never get the design. Okay, but however, you can find the equivalent form of these circuits by doing some experiment. Okay, that means that do some experiment to find out what is VTH and RTH. Okay, then actually you can still analyze the load properties of these circuits. Right? You'll see that in the experiment. So first steps of Thevenin's theorem says that you remove this load. Okay, when you remove this load, then you get these circuits. To find VTH is to find the open circuit voltage after removing the load. Right? After removing the load, you can see that if you don't have this load, then your VTH, right, this is open. Your VTH will be your VOC. Because no current flow through it when it's open. So no voltage drop, right? So VOC is your VTH. Okay, so remember this. This is the first step. Remove the load, leave it open, find the voltage across the open terminal, and that's your VTH. Now, to find RTH, more steps are involved. Also, it's based on the circuits with the load removed. Okay, additional step is required. Set all the independent sources to 0. Now, this is how I remember it. If it's a voltage source, I set it to 0, right? Turn it off. Now, how do we set a voltage source to 0? Short circuits. Short circuit means 0 resistance, right? 0 resistance means multiplied by any current, you get 0 volts. So this short circuits. On the other hand, with a current source, make current source equal to 0 by open circuits. If it's open, no current can flow through it. No current can flow through it. Therefore, the current will become 0. So very easy to remember. Just set it to 0, right? And figure out how do you set it to 0. Voltage source short, current open, right? Okay, if there's only independent source, that means no dependent source, no control source, then it's very easy to determine the equivalent resistance. Go back to last week, just simplify using series parallel, right? And use Y delta only when necessary, right? Do not start to use it immediately. Only if you simplify halfway or you cannot simplify any further, then you start using Y delta delta 1. Okay, let's look at these circuits. This is the original circuits. Okay, there's only independent sources. Right? That's why I start from this question first. I'm jump to question 4. Okay, I'll come back to question 3 later on because this is easier to understand. There's no dependent source, only independent source. Right? This is a dependent source, constant. Correct? This is a dependent source, constant voltage. This is a dependent source, constant voltage. Now, how do we set them equal to 0? Right, first, we must remove the loads. Right, remove this load, and this is what we get. How do we set this voltage source equal to 0? Voltage equal to 0, you short it. Right, short it. Voltage set to 0 by shorting them. Right, as I said, V is equal to IR. Short means 0 resistance. So you get 0 volts. Okay. Now current source, you must open it. Right, that means that if there's a switch here, just open it, switch off. Then current will stop. No current will flow through any open terminal. Open terminal, in fact, means infinite resistance. Right? Infinite resistance. So your current become 0 when this is infinite. Okay? You can't flow through it anymore. Okay? When you open, it means that it's air, right? Infinite resistance. Okay, therefore, my circuits become this. I short these two sources. I open this terminal. Okay, after that, find the equivalent resistance across this terminal, right? Take note that it's across this terminal, okay, which means that as far as this terminal is concerned, right, you must simplify into one equivalent resistance. Okay? And we can see that this 3 ohms is in series with 5 ohms. Right? In fact, you can simplify this into this 8 ohms. Correct? 8 is equal to 3 plus 5 in series. Same current. No current flow through here. So all the current flow through here and here. Alright? So this 8 ohm. Now, we are interested in the resistance across this terminal. So as far as this terminal is concerned, 2 ohms is in parallel with 8 ohms. Right? You have 2 resistors which are in parallel. Okay, if you draw it this way, you can see something like this. 2 ohms and then 8 ohms. Right? Same voltage. So you get 1.6, which is 8 times 2 divided by 8 plus 2. 16 divided by 10, 1.6 ohms. So we have obtained the RTH, right? We need to find the VTH. Same thing, to find the VTH, you first remove the load, then determine the open circuit voltage. Okay, in experiment, sometimes you can just measure it directly, right? But in circuit analysis, we must apply circuit's law to find this VOC, the open circuit voltage. You use any methods that you want. Mesh analysis, nodal analysis, right? It's up to you. Okay, because we have just studied source transformation, right? So I'll use source transformation, but just an overview. If you want to use mesh analysis, right? For example, you can do this. Mesh 1, mesh 2. Mesh 2 is known, 6 ampere, right? So you only go run this loop. Just take note that this, right? In this loop, your current will be I minus 6, right? I minus 6. Okay? And then you can write down one equation in terms of I. Make use of I to find out this VOC by going around this loop. So this is one way. Okay, you can also use nodal analysis. Nodal analysis say assign node voltage. Maybe this V1, this V2. This is known, 0 volts. If this is 0, this is also known, 20 volts. Right? So you need to solve two equations. But the nice thing is that your VOC is then easier to obtain. It's just V1 minus V2. Right? VOC is V1, this node voltage, minus this node voltage. This node voltage, voltage at this node, minus the voltage at this node is the voltage across it, right? Which is your VOC. So any methods, right? Any methods. Okay, here we use source transformation because we just introduce these methods. Right? Perhaps it's good to review it. I'll transform this current source in parallel with 5 ohms into a voltage source in series with 5 ohms. The whole idea is that I put two meshes into one, right? Or you can just do mesh analysis directly because this is known anyway, all right? So it's up to you.
Sorry, Prof.
Yes?
Is the video recorded?
What?
Is this tutorial recorded?
No, I will not record any videos. If you want, you do your own recording.
Okay.
But please be careful with video recording. One thing I do not like is that video recording is something that you always think that I can always do that later. Right? But that day may not come actually. Or it may come when it's very, very late. So it's the same as sometimes we go somewhere else and stay. We always think that I'll have time to visit this place. Right? But suddenly you change your plan, you decide to go home earlier, then you miss the chance. So this is something that you need to be very careful, right? Video recording is good for you to review, but it's something that would also turns into bad things if you do not, right, use it carefully. Meaning that I'll view that later on. I'll view that after Chinese New Year. Then after that, I'll view that during recess. Right? Then you have other things you occupied with it. Then you say that I'll view it anyway before the exam. Then just too late. So be careful about that. Okay, remember what I said. Every week, be consistent. Make sure that you can do all the tutorials without looking at the solution. If you look at the solutions, then it turns into a lectures again. Right? There's a difference between tutorials and lectures. Okay, as I said, if you want to learn the sports, no way that you can watch a YouTube video to learn a sport. You must practice, right? So this is the same system, lectures, tutorials. Right? Lectures, tutorial is the practice.
Yes, Prof.
So be careful of that. Right? So if you want to record, you just record it by yourself for your own reference. Yeah, but it's good that you attend this tutorial. Okay, let's move on. I was saying that we can use any methods, right? So there's no fixed step actually. That's why at this beginning stage, you should try to do as many methods as possible. Right? Try mesh analysis, try nodal analysis. Then it will tell you that which method should I use? Right? You can see that no fixed methods. It's the matter of how many variables that you have, right, and what you want to solve. Okay. So I use source transformations, but if you solve this circuit directly, also fine, right? You can get the same answer. Okay, and over here, notice the sign, right? This current should come out of a positive terminal. So therefore is positive terminal is this way, right? Because one sign wrong, everything will be wrong. So I've transformed my current source in parallel with a resistor to a voltage source in series with a resistor, right? Given current, time resistance, 6 times 5, 30, right? Easy to remember, right? Ohm's law. Parallel put into series, right? Okay, then I want to find this VOC. So I use mesh analysis. Go around this loop. Okay, for example, you start from here, plus 20, voltage drop across 3 ohm resistors, 2 ohms, 5 ohms, right? 2 ohms, 5 ohms, and from here, along this direction, there's an increase in voltage, positive 10, increase in voltage, positive 30. Now, if you do the other way around, it's also the same, negative 20 plus 3i plus 2i plus 5i. That means that you put this voltage across the resistor as positive, right? And then over here, negative terminal, you must put negative 10. Negative terminal, you must put negative 30. And then you come back to 0. Now you look at this equation, it's just to multiply this by negative, right? You get exactly the same thing. That's why I say that it's a matter of your own preference. Right? Fix one which you think, right, you can write down with accuracy, precisely, right? Okay, one unknown only. That means that I assign this mesh current I. It's this current I, right? And it's flowing through all places because this is open. And I solve for I, 6 ampere. But that's not what I want. I want VOC, right? You want VOC. Now, how do I VOC? VOC is 2I. Voltage drop across this resistor is 2I. Right? Minus 10 volts. I is 6. So 6 times 2 minus 10 give you 12 volts. Okay, if you cannot write down this directly, never mind. Take Kirchhoff voltage law around here. One loop. Right? Just focus on this loop. So from here to here, there's an increase in voltage. So right now, plus VOC. Right? Increase. From here to here, there's a drop in voltage, minus 2I. From here to here, there's an increase in voltage, plus 10. Then you back to 0, back to the same point. Right? Now you can see that this is exactly equal to this. You can even take this path, but here you have lesser components to deal with. Right here, you need to deal with 1, 2, 3, 4. But the answer will be the same. Right? In fact, if you look at these equations, it just means that if you bring this 2i and 10 to the other side of the equation, it just means that 2i minus 10 is equal to 20 minus 3i minus 5i plus 30, which is exactly this Kirchhoff voltage law along this loop, right? So it's very flexible. Use any method as you wish. Okay, I will just apply Kirchhoff voltage law around this loop. Okay, or if you are very familiar, just write it down directly. Right? If not, don't worry. Just use any method which you think, right, would be easier for you. Okay, but if you want to practice your accuracy, you should try the other way also. See whether you can get the same answer. So we have found VTH by finding the open circuit voltage after removing the loads. We have also found RTH, right, by removing these loads and determine the equivalent resistance. So now just use VTH squared over 4RTH. You can check it's 0.625 or 625 times 10 to the power of negative 3, right? Meaning 10 to the power of negative 3, it means that divide by 1000. Any questions? Okay, notice that there's another way of finding the equivalent resistance. Right, the idea is that after removing your independent sources, correct? Remember there was a voltage source here, V equal to 0. There's a voltage source here, set V equal to 0 by shorting them. There's a current source here, I open it so that my current is equal to 0. And this is the equivalent form. Now some of you may be confused, right? Why do I say this is parallel with this? Okay, if you apply a voltage source across here, then everything will be clear, right? Over here, you can see very clearly that this is actually in parallel with 8 ohms, right? As far as this voltage source is concerned. Now, these methods, you can also find your equivalent resistance. Okay, the idea is actually very simple. Imagine that you have some pipe systems. You are not sure, right, whether the resistance is high or not, namely whether is it choked seriously or not. So what you do is that you go and pump in something with a known pressure, right? If the pressure is known, and if you can measure the flow rate, then you can actually determine the resistance. So it's actually the same over here. If I want to find out, right, what is the resistance, what I need to do is that I pump in the known voltage, then I determine the flow rate. Now in experiment, you just measure the flow rate, correct? Connect a source, measure the flow rate. In circuit analysis, you calculate the flow rate. And V over I is equal to resistance. This means that instead of finding the resistance directly, I find it indirectly by using the voltage and current. Okay, usually we put 1 volt. Why? Convenient. If voltage is equal to 1, then 1 over I is your resistance. Now, can it be 2 volts? Yes, because this is a linear circuit. You put 2 volts, your current will be times 2. Then when you divide, it's still the same resistance, right? So this is for linear circuits, right? Remember, this is for linear circuits. If you look through your Thevenin's theorem again, the assumption is that it must be linear. Okay, next is that then I need to calculate this current flow, right? And you can see that this is equivalent to finding this current, let's call it I1, and this current, let's call it I2, and then add them up, because I is equal to I1 plus I2. And what is this current I1? Just Ohm's law. Now 1 volt is applied across the 2 ohm resistor now, correct? So 1 volt divided by 2 is I1. And 1 volt is also applying across my 8 ohm resistor. So therefore, 1 volt divided by 8. Okay, and you can see that this is exactly something like adding up the conductance, right? Adding up the conductance, and RTH is 1 over I, is exactly 1.6 ohms. So this is another way of finding it. Okay, but this way you should use it if there's a dependent source. If there's no dependent source, you should use series parallel to simplify it, right? It's easier. But in the event that you're not sure whether they are series or parallel, put a source across them, then everything will be clear, right? Everything will be clear, and then you can proceed. Now, R is equal to V over I. This means that I can also put in a current source, say 1 ampere, then calculate the voltage across it. It's also the same. So in this case, I'll calculate the voltage across this, right, rather than the current. But the rest is the same. Now you should go back to try this, right? to go back to try this, 1 ampere, use current division law to find the current flowing through any of the branch. Once you know the current, multiply by the resistance, you can get the voltage. So the method is not fixed. Use any method as you wish. Sometimes it's more convenient to put a voltage source. Sometimes it may be more convenient to put a current source, right? So it depends on the circuit configuration. So I hope everybody get the ideas. If you have a circuit, we should not share the resistance. So what you do is to pump in the source, measure the other variables, or calculate the other variables, and then use Ohm's law to calculate the resistance indirectly. But take note that this method is only useful when you have a dependent source. Okay, as in this case, we have a dependent source. Now you cannot remove the dependent source because why? There are resistance, right? It's a component. There's a resistance in it. If you remove it, you're removing its effect. That means removing the resistance of it totally, and your circuit will change. So the whole idea is that I have a source with unknown resistance, right? I do not know the resistance, so I pump in something, and then I determine the flow rate. I pump in 1 volt, determine the flow rate, and I use 1 volt over I to calculate the resistance, right? So as I say, it's like when the pipe, you're not sure, right, how much resistance, you pump in some pressures, determine the flow rate, then you can get the resistance. So let's go back to question 3. Just now I've jumped to question 4 because this question has a dependent source, which is depending on the voltage across the 10 kilo ohm resistors, right? So in this case, when you simplify the circuits by turning off the voltage source, do not turn off this, right? Do not turn off this, leave it there. If you remove it, it means that you basically ignore the resistance of that component. So we set the independent only to 0, and this is our circuit now. Okay, to determine the RTH, we pump in the known voltage of 1 volt, and we want to calculate this current. 1 volt divided by current will be your RTH. Okay, after that, treat this as a circuits, new circuits, and use any method that you want to solve it. Okay, I'll use nodal analysis, but you can also use mesh analysis. Okay, nodal analysis says that assign node voltages, but here this is 0 volts. This is 1 volt, right? So 0 plus 1. This node voltage is known, 1 volt. This 0 volts, this part is shorted, so this is also 0 volts, right? If this is 0 volt, this is plus 4V0, so this node voltage is plus 4V0. Okay, therefore, the only unknown is this plus 4, is this V0. Okay, and therefore, you can actually solve this very easily. Okay, I'll just use Ohm's law. Okay, indirectly, it's actually nodal analysis. Inflow equal to outflow, right? Our current I is this current I1 plus I2. I1 plus I2. Then I1 is just the voltage across these resistors, okay, which is 1 volt minus 0. Right? Remember this 0 volts, this 1 volt. 1 volt minus 0 is the voltage across the resistors from high to low current flow this way, I1. So it's 0.1 milliampere, right? I1, just Ohm's law. Now, in this I1, you do not need to care about this because this is used at I2, right? Used at I2. So let's move on to I2. I2 is now equal to 1 volt minus 4V0, the node voltage, is the voltage across it, divided by 20K, give you the current flow through it. And this is my I2, right? This is my I2, but I have a problem, I have V0 here. Then you trace back, where is V0? V0 is here. V0 is here. Okay, V0 is actually negative 1 volt. How do I know? And this is 0 volts. All right, connected to ground. This is 1 volt. So 0 minus 1 is the voltage across in this direction. 0, right, minus 1, plus and minus. 0 minus 1 is 1 volt. So I get this voltage across it as negative 1 volts. Okay, the other way, if you're confused, just draw this 10K here. And then notice that the convention is this way, all right? Negative connect to 1 volt, 0 connect to here. Then if this is 1 volts, this, the other way around, should be negative 1 volts. Okay? You can write it down directly. Okay, if you're still confused, then Kirchhoff voltage law, one round. Here I have plus 1 volts, right? Increase 1 volt. Here I have plus V0. So both plus, right? Increase and increase. Increase, increase. I back to 0. So V0 is still negative 1. So many ways, right, to do it. Just choose one which you are more comfortable with. In any case, you can conclude that V0 is negative 1, then just plug it into here and continue, right? And we can check that I2 is 0.25 milliampere. So we have found I1 and I2. Then we add them up. By Kirchhoff current law, we can find I. So I is equal to I1 plus I2. Sum them up. We get 0.35 milliampere and 1 over I, 1 volts, right? We applied 1 volts. We applied 1 volts to these circuits and we determine the flow rate. We found that is this. Right? So 1 volt divided by this flow rate is the resistance and is equal to 2.857 kilo ohms. Any questions? So I hope everybody get the ideas, right? We do not know the resistance of this component. So we pump in something there, right? Determine the other variables and then find the resistance. Okay, I suggest that you go back and try this. Try use current source. Try use current source. Now, if you have a current source, then use any method to solve it. Okay, you can see that here, basically, if I solve it, I'll use nodal analysis. Right, nodal analysis because there's a dependent source here. I cannot use current division law, right? So I use nodal analysis, only one node voltage V. Okay, one node voltage V. And then you apply Kirchhoff current law at this node. This is 1 ampere. This current is V divided by 10K. This current is V minus 4V0 divided by 20K. Then you need to relate the V0 to the node voltages, right? So if this is V, if this is V, then this is V0, right? It's the other way around. So you can see that V0 is actually negative V. Right? Just now it was 1 volt, so negative 1, now your V is negative V. Okay, that means that you can express this in terms of the node voltages only, and then find V. Right, you can go back and try. Right, you should try many methods so as to get familiar with it, because when it comes to solving Thevenin's theorems, right, you need to decide the method to use. So if you are familiar in deciding which method is easier to use, right, it will be helpful. Okay, we have only found RTH, right? By removing the loads, pump in the known source, calculate RTH indirectly. Now is to find VTH. Remember, to find VTH is just to find the open circuit voltage across this terminal. So again, you need to use any method to solve these problems. Okay, you can use mesh analysis, apply mesh current this way. Let's call it I. This means that this is I. Then Kirchhoff voltage law, you write down one equations, plus 70 voltage across 10 kilo ohms, right? Ohm's law, voltage across 20 kilo ohms, Ohm's law. Here to here, there's a drop, positive to negative, put negative, for 0. Okay, this is not in terms of I, right? Not in terms of the mesh current, but you can go back to V0 and check. V0 is just 10 kilo ohms multiplied by I, okay, which means that you can express in terms of I, then put it back into here. There's only I. You can solve for it directly. It's 1 milliampere. Right? So this is the idea of mesh analysis of assign mesh currents. Write down an equation in terms of the mesh current. Anything that's not in terms of mesh current relate to it. For example, your dependent source, right? V0 is related to I by Ohm's law. Then just put V0 in terms of I. Then you have one equation with one unknown only. Okay, lastly is to find VOC. Right? To find VOC, you can either write down this directly or go one look around any of the mesh. Okay, over here, for example, maybe I go the other way around. Right? Increase will be VTH. This is what I want. You know, over. Okay, maybe I go the other way around because my I is defined this way. Right? Clockwise, sorry, clockwise. So clockwise, then maybe I start from here. Clockwise, right? Increase 70. From here to here, plus. Okay, over here, drop 10 kilo ohms multiplied by I, right? And over here also drop minus VOC or VTH. And you come back to 0. Okay, this will give you this as well. If you bring VTH to the other side, 70 minus 10K I is 1 milliamperes, therefore VTH is 60 volts. But you can also try this round this way. Write down equation in terms of VOC, in terms of these two. Right? In fact, as I said, you can see from here that this, right, is equal to these two. So they are the same. Right? Same potential difference, which is this VTH. Any questions? Okay, therefore we have found the VTH 60. Okay, we have found RTH, and now with this simplified circuits, actually, what you can do is that you connect any load to it. Right? You can do the analysis in an easier way. So Thevenin's theorem is a way of simplifying the circuits to a form which is easier to analyze, and it is particularly useful in calculating the maximum power. Okay, once you see a question with maximum power, right, do not need to think. The only way out is Thevenin's theorems, right? It's easier to solve that way. Any questions? Okay, let's look at the last questions. Okay, we have op-amp, right? Many students have difficulty with op-amps. Let me try to show it to you that it is not that difficult once you understand, right, the main ideals, which is your op-amp characteristic. Now, firstly, we look at the problem. We want to find the gain of this amplifier. This is your input, actually, which is your Vs. This is your output, which is your V0. So output over input is the gain, right? It's just the gain of this amplifier. Now, right, let us review the properties of amplifiers. Okay, it has these three properties. Okay, but you do not need to remember this. You must remember the result of this property, which is this box, right? I'll come to that later on. Okay, firstly is that is assumed that this ideally, right, is zero output resistance. Okay, if there's no voltage drop here, then your V0 is directly equal to this voltage, okay, which is the gain multiplied by input, right? Gain multiplied by input. The input is differential, plus minus. It means that V2 minus V1. right? V2 minus V1, multiply by gain, give you output. If you bring the gain to the other side, you get V0 divided by A. Now, ideal op-amp has very, very large gain. So this means that, right, this is approximately equal to 0. It means that V2 minus V1 is approximately equal to 0. So this gives us the first property. V1 is equal to V2, right? Namely that this V1, V2 will be the same. So it's easier to put this V connected to the positive terminal as V plus, V connected to the negative terminal as V minus. In fact, it means that V plus is equal to V minus, right? This is the first property. Now the next property is because there's infinite input resistance. If this is infinite, no current can flow through it, right? Insulator. It means that I1 is 0, I2 is also equal to 0. Or if you put it in terms of plus and minus, it means that I plus, I minus are both equal to 0. So only this one you need to remember, and it's very easy to remember. V plus equal to V minus, I plus equal to I minus equal to 0. Okay, then if you impose this property on your circuits, then you can solve it easily because it gives you the information about the current and the voltage, right, of this op-amp. Now in circuit analysis, if anything that you do not know, you assign a variable there. Here we have two op-amps, op-amp 1, op-amp 2. So therefore we need to differentiate them. I put this as V1 minus, op-amp 1 negative terminal. I put this as V1 plus, right? Op-amp 2, op-amp 1 positive terminal. So similarly V2 plus, V2 minus. Okay, similarly you can also put I1 minus, I1 plus, right? I2 minus, I1 plus, I2 plus, I2 minus. So this is actually to assign the variables to the circuits if we do not know. Now next, okay, I want to solve it using circuit analysis. So I can use nodal analysis actually, because if I assign this as V1 minus, this means that this node voltage is V1 minus, right? This node voltage is Vs because this is 0 volt, 0 plus Vs, right? This is Vs. Okay, how about this one? 0 volt plus V0, so this is V0. Now this node voltage is not known, so I call it V2 plus. This node voltage is not known, so I call it V2 minus. Right, so I have assigned all the node voltage. Then I can apply Kirchhoff current law at any node. For example, this input node. If you apply Kirchhoff current law, inflow equal to outflow, the current flowing through this resistors, right, is Vs minus V1 minus, right, voltage across them, divided by R. Now, outflow, there are two here. One is V1 minus, minus V0, this is V0, this is V1 minus, right? Voltage across them, V1 minus minus V0, divided by R, outflow. Similarly, V1 minus, minus V2 plus, right? This V2 plus. And this is the equation. Okay, and after that, notice that I need to impose this op-amp property. V1 minus is equal to V1 plus. But V1 plus, take note that it's connected to ground. Right? So V1 minus is equal to V1 plus, which is equal to 0 volts. Okay, if you put it into here, this will be equal to 0. Right? This will be equal to 0. Then this will also be equal to 0. I'm just imposing the op-amp property. And the denominator, R, are the same. It can be cancelled out. So basically, this is what we get. Right, the next equation. So basically, we simplify the first equations into this equation. Now recall that your objective is to find the gain, output over input. So these two are okay, but we have one problem. Right? we have this V2 plus. So trace V2 plus, V2 plus is here. And according to the op-amp property, we know that V2 plus is equal to V2 minus, correct? V2 plus is equal to V2 minus. And over here, we also impose this property that this current is equal to 0. Right? This current is equal to 0. Just now over here also, we impose this one. The current I minus is also equal to 0. No current flow through here. So here, also no current flow through here. Okay, if there's no current flow through here, then imagine there's a current from here. And when you come to this junction, no current can flow inside here. All the current must flow through here. Okay, therefore, they have the same current, which means that these two resistors are effectively in series. And therefore, you can use voltage division law to find this V2 minus. Right? You can view it this way. V0 is divided. V0 is divided according to the ratio of the resistance. They are equal, so half. You get 0.5. Now, if you want to continue with nodal analysis, it's also fine. That means that you cannot visualize how to use voltage division law. Never mind. Apply KCL at node 2. Right? We applied KCL at this node. Now we need this information, V2 plus. Right? They are equal. So we apply at this node. So this is actually my V2 plus, correct? Which is also my V2 minus. So I just call it directly V2 plus. And this node is V0. This node is 0 volts. Okay, if you apply KCL at this node, then if I call this inflow, this is basically equal to V0 minus V2 plus divided by R. Right, inflow. Now this is 0. This is 0, so no current can flow through it. So the only way out is this one. This is my outflow. And it's equal to V2 plus minus 0, RN connected to 0, right? Divided by R. Because they have the same resistance, right? You can see that you get the same relationship, right? Which is V2 plus is half of V0, right? Because V0 is 2 times of V2 plus. So either you use voltage division law or you apply nodal analysis again. Like this is the node voltage V2 plus. Take KCL at this node. You can write down the same equation. Okay, and the idea is that I now relate my node voltage, right, to the output. So I can now combine them. Put V2 plus into here. Okay, I get this value. And everything in terms of V0 now. And Vs, then I can get the gain. So Vs output over V0 output over Vs input is equal to negative 0.667. And this basically means that if I apply 1 volt here, I get negative 0.667 in my output, right? So if I apply 10 volts, you get 6.67 negative. So two observations here. First is that the gain is less than 1, attenuation. Secondly is to take note that there's an inverse of the sign, right? Positive become negative, negative become positive. Any questions? So remember, for op-amps basically is to impose, right, all these properties of op-amp. V plus equal to V minus, I plus equal to I minus. And after that, basically it gives you some information about your node voltages and your current, right, with respect to the op-amps. Okay, after that you can treat as if the op-amp is not there. Right? But just impose this property. This is actually 0 volts. This is actually 0 volts. Because of op-amp property. No current can flow through here. No current can flow through here. And because these two are the same, This is actually V2 plus, and then you just analyze the circuits. Any questions? Okay, next week, right, Chinese New Year, as you know, no tutorials, and it's very hard to arrange a common time slot, so I have to do it in Saturday, right? Saturday, using Team, only online, okay? Which means that you can access the same link given in the tutorial website. We'll do it Saturday at 3 p.m. And I wish everybody a happy Lunar New Year or happy holiday. Thank you.
Thank you, Prof.
Thank you, bye.
Thank you, Prof.
Thank you.